This supplementary video is to kind of aid you in our discussion and development of Kepler's 3 laws that we did in class today. So he has 3 laws. Again, Kepler collected with his cohort Tycho Brahe an enormous amount of data on celestial bodies and their movements and just tracking. So just ridiculous amounts of data. And by analyzing all this data, he used empirical evidence, which means data, to develop these 3 laws. So he didn't know why they did what they did. It took Newton to come along and with his universal gravitation to explain the why behind it. But it was a great accomplishment to collect this data and be able to come up with these 3 laws. So the first law that he has, Kepler's first law, is that all orbits are elliptical with the sun at one focus. So what we have done so far is to assume circular orbits, which is great because we're kind of doing baby physics and it's a little bit easier. But more advanced physics will look at the elliptical orbits and apply Newton's law of universal gravitation to that. But so for what we need to know, what I want you to focus on and just basically conceptually understand is how do we go from a circular orbit to an elliptical orbit. And basically if you have some satellite that has orbiting some central body, we call it the parent body. This could be the Earth going around the sun or perhaps some artificial satellite orbiting around the Earth. What happens to the orbits when the speeds increase or decrease? Well, the answer to both of these questions is that they become elliptical in nature. So we just want to look at what does the structure look like if we increase or decrease. So if we look at the first case where we increase the speed of the satellite. So the satellite is right here orbiting around a central body and it fires the booster rockets, and what's going to happen? Well, if you can kind of think about circular motion, if I go to a greater speed, its inertia is going to want to take it outside the path, and that's exactly what happens. It begins to go outside the path and it traces out this elliptical orbit. And again, I'm exaggerating the orbit, but eventually gravity from the central parent is going to pull it back in, and it's going to come around and back here, and it just touches just at that one point. The sun will remain where it's the fastest right here, where we've increased the speed. We call that the perihelion position. The sun again is at one focus. The other focus would be over here. As the satellite orbits around, the speed will decrease, and then gravity is going to start pulling it back in and whip it around. We'll talk more about how to calculate these different speeds when we get into conservation of angular momentum and conservation of energy. The second case that I would like you guys to understand is what happens if we decrease that speed. So again, here we've increased the speed. Now let's say we decrease that speed. Well, again, think about the circular motion. It doesn't have enough velocity to maintain that circle. So that elliptical orbit, again, there's my focus, there's my central parent, it's going to kind of fall inside there. So it's almost like it's falling into the central parent planet, and then gravity is going to whip it around and carry it around. And that's not the best ellipse that I've ever drawn, but you get the idea of what that elliptical orbit is going to be at. So now the central parent here is at the far end. This, where it's moving the slowest, we call it the aphelion. And as it whips around here, this would be the perihelion position of the satellite. So it's always the fastest when it's closest to the parent body or whatever it is orbiting around. So that's Kepler's first law. Kepler's second law will be a little bit quicker. This again comes in more when we're discussing angular momentum. It's not a big thing that I spend a lot of time on. But basically, if the sun, and again, we're looking at the sun and perhaps the Earth orbiting around it, this is the central body. If I were to extend a line from the focus of the ellipse out to the orbiting body, and as it sweeps out time, and we'll call this equal times months, it would be the unit of time here, but whatever that means, it means that it sweeps out in equal areas in equal amounts of time. So each month, if I were to calculate that area, it would be equals amounts. So that's Kepler's second law. There's not too much that we'll be doing with that in this unit. The third one is the one where the money is. This is a derivation that you should all be able to do. But again, Kepler's third law of periods, Kepler came up with this idea, again with that enormous amount of data, that if I take the ratio of t squared to r cubed, it's going to equal a constant for any set of objects that orbit the same parent planet. So what examples can we think of that? That would be artificial satellites orbiting around the Earth. It could be the planets orbiting around the sun. It could be moons orbiting around any other planet. So any of these, what we mean by that parent planet, again, it's the one, they share that same object that they're orbiting around. So for our Earth, it would be the sun. So Earth, Jupiter, Mars, etc., all orbiting around. They would exhibit this ratio that t squared over r cubed is constant. So what does that mean? T is the orbital period. And since we're just looking at a ratio of these constants, you can really use any units. You don't need to be in SI units anymore. You could be in months, and then you would solve for the period for the other object also in months. And the orbital radius, again, could be any units. So if I were to set up a ratio here, t squared over r cubed, you could set that equal to t squared over r cubed for any other planet. So example, this could be the Earth, and this could be, say, Mars. Okay, and that ratio, t squared to r cubed, would be the same for both of these because they both orbit the sun. So that's the application of Kepler's third law. So that's kind of that idea. But what I want you to be able to do is to derive Kepler's third law using Newton's law of universal gravitation. So that's what I want us to go through right now. So again, all of our derivations are going to start with Newton's laws. So F equals ma. Again, we're talking about circular motion because we're talking about orbits. This net force that's acting on it is going to be the force of gravity, and that's going to be equal to m, and we know the definition for our centripetal acceleration is going to be v squared divided by r. We have a very elaborate expression for this, Newton's law of universal gravitation, that stands for this, and that is big G, universal gravitation constant. I'm going to make big M to be the central body, or the parent planet, little m, and then this r squared here is going to be equal to m. This will be the thing that's moving in the circle, v squared over r here. This m is going to cancel with that m. This r will cancel with one of those r's, and I'm left with gm over r is equal to v squared. Okay. We know that our velocity, again, we want to get things in terms of the period and the radius, so I got to get rid of this velocity term. I know that v for anything moving in a circle is going to be 2 pi over t. So v squared is going to equal 4 pi squared r squared over t squared. To be continued on the next page. Get a next page here. And I'll set this up so you can kind of see my work a little bit. There we go. All right, so I'm going to substitute that in, and I get gm over r equals 4 pi squared r squared over t squared. I'm going to cross multiply, and I get gm over t squared, times t squared, equals 4 pi squared r cubed. And we can see that t squared and r cubed has come together. I'm going to put both of them on the same side of the equation, and I get 4 pi squared g big M. So we can see that all of these are constants, 4 pi, and the universal gravitation is constant. This m, again, represents the parent, the one object that they share. So it says that the ratio of t squared to r cubed will remain a constant. And that's Kepler's third law expressed as that ratio of t squared versus r cubed. Okay.